This is what we call the anaerobic workstation for the microbiology lab.
The following is a video presentation of the Whitley A35 anaerobic workstation. With 30 years of experience in designing workstations for a variety of applications and having listened to our users, the Whitley A35 anaerobic workstation is born. This latest incarnation fulfills the diverse needs of both our research and clinical customers. From a relatively small footprint, we have been able to maximize incubation capacity to create the perfect environment, whether for a few plates or hundreds of plates. The Whitley A35 anaerobic workstation is the latest innovation in workstation technology from Don Whitley Scientific. Complete with a built-in rapid airlock and intuitive touchscreen control panel, this new workstation allows you to work completely glove and sleeve-free. The A35 is the first workstation to be offered with our new gloveless, sleeveless system. Sample manipulation within a secure anaerobic environment is now as easy as working aerobically on the laboratory bench. The working and storage areas of the chamber are temperature controlled with an impressively low gradient throughout. This allows the full internal volume to be used as an incubator if desired. To gain access to the workstation, open the outer door. Insert your hand and begin working. When finished, withdraw your arm slowly. Tuck in the flap and close the door. It's that easy. The A35 is available with an optional removable front. Simply release the latches surrounding the perimeter of the front shell and using both hands lift the front away from the cabinet. This feature facilitates easy decontamination between experiments and the introduction and removal of large pieces of instrumentation.
One thing, okay, I will show you on the temperature display on the top there. Basically that's what is showing 37 degrees, which is is normal the body temperature. That's what we normally like to set it.
The A35 is equipped with a transfer airlock to introduce samples or equipment. The 12-liter rapid cycle airlock has the capacity to introduce up to 40 petri dishes in 60 seconds. There is also the option to specify the 15-centimeter letterbox, ideal for quickly transferring all sizes of dishes and small items. Operating the airlock is very simple. Open the outer door and introduce your samples using the tray, then close the door. Initiate the airlock flush sequence by depressing the icon on the touchscreen. After 60 seconds, the sequence is complete. Depress the blue button from within the workstation to open the inner door. Using the hook, pull the tray from the airlock into the workstation. The A35 utilizes an innovative touchscreen interface with password-protected user levels to prevent unauthorized changes to workstation conditions. Temperature and humidity are readily defined by the operator, and a history of workstation conditions can be seen at the touch of a button. You can easily download stored temperature, humidity, and internal pressure parameters over the last 30 days via any standard USB flash drive. 1 or 2 storage trays can be positioned under the shelf. This is either a factory fitted option or trays can be fitted on site. The dehumidification system automatically removes excess moisture to a reservoir outside of the workstation. Water collected in the reservoir is evaporated via a bacteriostatic wick. The standard cable gland allows cables and probes to be introduced into the chamber without compromising internal conditions. More than 1 gland can be fitted. Glands to accommodate larger diameters are available. An optional vacuum port is available for the removal of liquids from within the workstation. Thank you for watching this video presentation. Please do not hesitate to contact Microbiology International for additional information.
Totally amazing, excellent discovery. All right, so this is like a 2-person koi chamber. It's flexible. See, it's designed to do anaerobic work, microbiology, basically. So the way that it functions, I'll show you really quick. If you look inside, so the first thing you can see probably is there's a sensor there. So that sensor is just indicating to you the oxygen concentration on the left and the hydrogen concentration on the right. As you can see at the moment, they're both 0, which is actually problematic. So oxygen should be 0. That means that we're anaerobic, but hydrogen needs to be somewhere around 1 to 2%. And the reason that it needs to be 1 to 2% is that the mechanism by which the chamber removes oxygen is by reacting hydrogen with oxygen over a catalyst. And the catalyst is contained within these they're called cat packs or cat stacks, as you can see here. So this is basically just a big box that has a fan in it. There's a fan on the ends here, as you can kind of see with the little grate. And this fan just continuously cycles air in the chamber through this screen on the front, as you can hopefully see there. Inside that screen, there's catalyst. And this catalyst takes hydrogen and oxygen, reacts them together to form water. And so there's also desiccant inside of that stack there. And that desiccant then absorbs the water. And so this is the mechanism by which you continuously remove oxygen. Oxygen not only diffuses through the walls of the chamber, as you can see they're made of plastic, but also comes in through the door, which is over here. And you can probably see there's another catalyst pack back there. So there's 2. It's a fairly large chamber, so you need 2 to keep the thing fairly anaerobic. Okay, so the door, this is called an airlock. It's got 2 doors, as you can see, basically so that you can make the environment inside anaerobic, and then open the inside door to take things in and out, and then close the inside door before opening the outside door so you don't let air in all the time to keep things relatively anaerobic. Okay, so as I said, we have this problem that the hydrogen concentration is 0 at the moment. We need to get that back up to about 1. And as you can see, if you look at our airlock again, the door is currently in aerobic state. That means that this outside door has been opened. So it says aerobic because there's essentially air in there at the moment. But before we can reload the chamber, the gas cylinder is empty. So I'll show you the cylinders. So there's copper line that runs from the back of the anaerobic chamber airlock all the way over to the gas cylinders, which are located here. There's 2 types of cylinders. This one is nitrogen. It's ultra high purity, so it has relatively trace amounts of oxygen in it. This one is a mixture of hydrogen and nitrogen, so it's 5% hydrogen, and the balance is the nitrogen. So it's not flammable at that point. But there's still some differences in terms of like the regulator because you're working with hydrogen. Okay, so if you can see up here, our hydrogen cylinder, although it's open, is currently empty. So we need to change the cylinder before we can use it. So we're going to do that real quick. Okay, so like that. So this closes the cylinder itself. I'm now letting the pressure off of the regulator. Okay, so this is loose, which means that there's not going to be any gas flowing through here anymore. But you see the pressure is still high, so you can relieve this little remaining bits of pressure by coming over here. I'll explain what I'm doing with this thing after a bit. Basically, you can manually operate the piece of equipment, but I'll explain that later. Okay, so we've now removed any leftover gases inside the regulator. We can shut the regulator off with this little valve here. I have to get a wrench. A cylinder that contains hydrogen, so it's backwards. So normally it's righty tighty, lefty loosey, so always just remember that it's opposite these guys. So I'm turning it to the right currently to take it off. It should be fairly straightforward. If you can't get it off turning left, then try the other way, I guess. But the nitrogen tank, which is here, is the conventional lefty-loosey. This case is opposite. Okay, so okay. So before moving the cylinder, you want to make sure to put the little cap on it. Now I always monitor the gas concentrations, or excuse me, the remaining gas volumes here. So this one's fairly full. It's at 2000 psi still. I think it comes around 2500. When this gets down lower, so maybe like 500, I'll order a new one. So for the hydrogen nitrogen mix, I already have a new one sitting here. So all we need to do is move it a little bit closer. Just want to make sure your cylinders are attached to the wall if you're moving them. Carefully. Okay, so you can show this too. If you're ever needing to know what's in there, you can always look on the label. It should say here. It gives you nice information in terms of composition. Here is also just a general type of cylinder, so it's 5% hydrogen. And then lastly, there's also this, certificate of analysis that Praxair provides, which let's see. Can't see it because it's all folded up, but in there we'll tell you the not only the requested concentration, but the actual concentration is measured by, I think, a GC in this case. So. This strap to the wall before you do anything. A lot of times these little caps come off. Not there's a tool in the lab. Usually it's in 232 by the human. But basically that tool has a little hook on it that you hook to the little hole and you can open it. Right, so just this little thermoplastic thingy here you can take off. Again, to the left, you get in one. I can show you this too, but the regulator also has an indication that this can be used for hydrogen. So if there's any question, you can always check or look up the type of regulator, which is also listed on there. Just make sure. Okay. So get it as you can, make sure it's on correctly with your fingers. And then don't go crazy with these. Don't tighten them too much. The nitrogen tank, you have to tighten a little bit more because it's a little bit more difficult to get them to seal. Okay, so we're going to slowly open the gas cylinder, and you see that the pressure is up near 2000 psi. At this point, it's important to check to see if there's any leaks, mostly just by listening. I don't hear anything. And then tomorrow, or even later this afternoon, I'll check to see if the pressure is still high. If it's going down rapidly, that means that we're leaking somewhere, which is obviously problematic. Okay, so we can open that a little bit more. We can also then turn our regulator on. Okay, so you see the pressure should be rising. We're going to put it up to 30. As you can see, there's a little indicator here that says that the gas mix should be less than or equal to 30 psi. That's just indicated by the company themselves. So I leave it at that. The nitrogen cylinder, as you can see, is listed here at less than or equal to 50 psi. The actual reading at the moment is a little above 50, but when the gas is flowing, it'll drop down. Okay, so that's how you change the cylinder. The same thing would apply to the nitrogen tank.
Just had an inlet right there. Just had a fall. I got it on video. That's the spice in the water. I just got it.
Okay, let's go back here after a short break, commercial break, I suppose. And yeah, so we need to basically refill the chamber at this point. This is still at 0. We just changed the cylinder. So what we're looking at now is the operating screen here. You can't really see anything other than this P9. Right, yes. So this actually says ready, and it has 0.0 inches of mercury. The screen is a little broken, so you can't read that very well. All it means is that it's ready to operate the program 9. So that's P9. You can run P1 through 10, but right now it's set for 9. And the current pressure inside of this is 0 inches of mercury. So it's atmospheric. It will go up, but it's actually pulling a vacuum on the inside. So I'll show you how that works. Okay, so P9 is just a preset program. That's what we use all the time. It pulls vacuum once, and then it fills with nitrogen. It pulls a vacuum again. It fills with nitrogen again. And it pulls a vacuum again, and it fills with the nitrogen hydrogen mix. At which point it will say it's anaerobic, and we can then open the inside door. Okay, so we need to do that before we open this, so we don't get a bunch of air into the chamber. So if it's ready, P9, we can just press start. Currently pulling a vacuum. You can see that it says vacuum. Okay. The pressure will decrease. It says it's increasing, but all the way up to 20 inches of mercury, essentially. You can't really see it. If you look, you might be able to come down here like this. Good. Anyway, that doesn't matter. Okay, so it now says purge gas cycle. You can't read it, so okay, so it'll then bring the pressure back down to near atmospheric by putting in our purge gas, which is just nitrogen. Vacuum again. You can look at this one. I mentioned that the pressure was a little above 50 before, so now the gas is actually flowing. The pressure is exactly 50. So you can just maintain it at that. This is also a good way to see which gas is flowing. You can watch the gauge change. So if you keep watching, it should jump here just a little bit. So the pressure is a little bit higher now. So that just indicates which one's going. So then you can come over here. Because we just changed this cylinder, pressure is a little bit different than where it started. We'll see what happens when it actually starts to flow. Turn this up. Okay, so that's now going to fill the chamber, which you can come back over here. At this point now it says gas mix. So there's gas in there somewhere. And mix here. Which helps you to know which one it's actually doing. So this is the final cycle. At the end of the cycle, it will beep. Once it reaches no vacuum. Okay, so beeped. And now you can see this says anaerobic. So before it said aerobic, now it's anaerobic, meaning that it's relatively oxygen free inside of there. So at this point, you obviously don't want to open the outer door, or else you have to do the whole thing over again. But we can open the inner door. So carefully, let's put our hand in here. Open the door just like that. And we're going to leave that door open because we're actually going to refill the chamber to get the hydrogen concentration back. So I'm going to teach you how to use manual mode now, which is actually fairly easy. So you can come back over to this screen. So previously we just used the start button to start the process there to make the chamber airlock anaerobic. Now we're going to manually adjust or pull vacuum and insert gas. So in order to do that, we press menu. Now it gives you like 4 options here. You can't really see these ones, but that's okay because all you need is this one, which says start will take you to manual mode or M mode. So press start. Now it says manual mode, up equals vacuum, down equals purge gas, start equals mix, and menu equals exit. So at this point, if we press menu, it gets us back to P9. I'll have to do that again. It's going to go through our little description again. So now at this point, we can do whatever we want. So we can press up to pull a vacuum. We can push down to do the purge gas, or press start to do the gas mix. So example, that's purge gas. It says purge gas. This gas mix, and it says gas mix, and then our vacuum. So we're actually going to leave the inside door open, and we're going to pull a vacuum. What that's going to do is pull the contents of the chamber out into the room. And in doing so, we can empty the chamber and then refill it. So do that. Okay, so we've been pulling vacuum now for a few minutes, I guess, and evacuating the contents of the chamber. I didn't mention before, but I wanted to make a note that the chamber contents are literally just evacuated right out the back of the airlock here. And so what that ends up doing in this room is it sort of accumulates right here in the corner. And I'm always a little bit nervous about the fact that a bunch of gas that doesn't have any oxygen in it is coming out here. So I usually open this window right here to get some fresh air as I'm standing here so I don't pass out. I don't know how much of a concern it really is, but I'm just nervous. Okay, so if you look at the chamber, you can see at this point it's actually quite sucked in. It's not puffed up like it was before. And this time I did actually pull a pretty significant vacuum here. So I really removed a good portion of the contents. And the reason I did that is because the hydrogen concentration is so low. If it were, say, at 0.8 at the moment or something, you wouldn't have to pull nearly as much of the gases out. Okay, so now that we've got a vacuum pulled on, we can fill it back up with mixed gas. So if you recall, the up button is for the vacuum, the down button is for the purge gas, and the start button is for the mixed gas. So we're going to just push start, and as you can see what it's doing, it just says gas mix. And it's simply going to pump the chamber full of gas. Okay, so we just finished filling the chamber with the gas mix. As you can see, it's now puffed back up, and we are at a hydrogen concentration of 1.6%, which is sufficient for our needs at this point. So now it's fine. We can just leave it. Before we leave it, though, we should shut this door. Have 2 barriers to the outside, just in case somebody were to open the outside door. And the other thing is that we need to change it back to the regular mode. So it's currently manual mode still. So if we press the enter menu button, we can get back to our P9 mode, which is our pre-programmed cycle for purging the airlock. The airlock is still anaerobic at this point. So if you wanted to, you could take something out of the chamber, put it in the airlock, and then take it outside. Or if you want to put something in, you're going to have to open this door, and it's going to become aerobic at that point, or you put it inside. So I think it's fairly straightforward about how to get something in, but I just mentioned really quick. If you didn't want to put something inside at the moment, you want to open this door. You'll then place the materials inside. You'll close this door, make sure that it's latched. And then you press start to run the 3 vacuum cycles and then the 3 gas purge cycles, at which point it will beep and say it's anaerobic. When it's anaerobic, then you can, with the outside door closed, you can open the inside door, take the stuff into the chamber, and then place them inside, and then again close the inside door. A few things to mention are that so it does pull a vacuum of 20 inches of mercury, which is fairly significant. So for typical things that are sealed, like media bottles and stuff like that, I will loosen the cap just to allow gas to exchange. It probably helps to remove oxygen as well. If you were to ever bring warm media in here, so let's say you took something out of the autoclave and it was still decently warm, you need to remember that under low pressure inside of a vacuum, it may have a tendency to boil. So don't do that because it's bad. And I know based on experience, so don't put it inside. And other than that, the only other thing to mention is that right now it's sort of confusing time because as you can see, we've come back to the P9 screen. Do you see the screen? There you go. And we know that it's anaerobic because we were just working with it, but at this point, it doesn't actually tell us that. So if somebody new were to come in, they would have really no idea whether it's anaerobic or not. So my philosophy is just always assume that it's aerobic. And if you want to open the inside door, you need to run the cycle, unless you know for sure that it is. For example, we know now that for sure it is anaerobic. But if somebody new were to come in, they should assume that it's always aerobic so that you don't pump the chamber full of oxygen, because that could be bad. Okay. Other than that, I think we're okay.
What about what are the other programs?
If anytime there's a problem. So let's say, for example, you put media in there that's hot and you're running the cycle and it started to boil. You want to immediately stop things and get the chamber open. So in order to stop a cycle in progress, the only way I know how to do it, at least, is to shut it off, turn it back on. That will immediately stop the vacuum or the gas purge, whatever it is. And at that point, then you can go back to the manual mode and adjust things accordingly. So if you have a partial vacuum pull, let's say 10 inches of mercury, you're going to have to shut the thing on, turn it back on, go to manual mode, and then purge it with a purge gas in order to get the door open. Because even a vacuum of a few inches of mercury on this thing won't allow you to open the door. So the door will be essentially shut. You won't be able to move it at all, even if you open the latch. So yeah, that's good. Other than that, I think that other things we can do.
Okay. Hope they learned that that's some sort of anaerobic chamber that is used in the the university hospital research and things like that. There are several sizes and shapes. All right. There's another kind that actually this one is portable ones. You're probably gonna see something like this in the news things. Okay. Let's take a look at this, how this thing works, okay, for the portable type.
PlasLabs, world leaders in acrylic containment and isolation technology. The PlasLabs 857 OTA One-Touch Go Anaerobic Glove Box is a completely sealed automatic anaerobic chamber. This new automatic anaerobic chamber allows the researcher to press the Go Anaerobic button on the touchscreen display to begin the purging process and create a strict anaerobic atmosphere. It features a color-operated touchscreen for automatically creating a strict anaerobic atmosphere. Other features include programmable catalyst heater unit and palladium canister, drying train system for moisture and oxygen reduction, quarter-inch hose barb gas connections for both nitrogen and anaerobic gas mixture, the PlasLabs bright light system, optical oxygen sensor, USB port for recording oxygen levels inside the glove box, an optically clear one-piece top, and a one-piece bright white bottom with rounded corners. The 857 OTA requires no installation and very little setup. To begin, place the programmable catalyst heater unit and palladium canister inside the glove box. Do not turn the catalyst heater on. Place the palladium canister next to the heater. For larger equipment, such as balances, shelving units, shakers, or stirrers, you may remove the clear acrylic top from the one-piece bottom. Using a quarter-inch hose, connect the nitrogen gas and the anaerobic gas mixture to the valves located on the back shroud. The anaerobic gas mixture consists of 85% nitrogen, 10% hydrogen, and 5% carbon dioxide. Once your desired equipment is inside the glove box and the gas is connected, you are ready to begin purging your glove box. The ambient conditions of your glove box can be seen on the touchscreen. The touchscreen display boasts many impressive features. Desired chamber to be purged, main chamber pressure levels and set point, transfer chamber pressure levels and set point, data logging for pressure levels and oxygen, password protection, oxygen analyzer. The oxygen analyzer is designed to read a percentage value until the oxygen levels achieve less than 0.5%, at which time the oxygen analyzer will read oxygen levels in parts per million. And the one-touch Go Anaerobic button to begin the purging sequence. A purging cycle consists of drawing a slight vacuum, -2 degrees of water column, and then filling with a gas to a slight positive pressure, +3 degrees water column. To operate, turn on the catalyst heater unit and place the thermocouple away from the heater. The heater temperature is factory set. Allow 5 to 10 minutes for the heater to reach its set point. Place the palladium canister on top of the heater. During the Go Anaerobic operation, the first 4 purge cycles use nitrogen gas. After the 4th cycle, the PLC switches to anaerobic gas. The PLC will continue this purge sequence until the oxygen levels are below 5 parts per million. Approximately 27 purging cycles make up the Go Anaerobic operation. Upon completion, purging the anaerobic chamber, less than 300 liters of gas will be consumed. The completely sealed design reduces the amount of gas needed to purge and maintain the anaerobic chamber. Your anaerobic chamber is now ready to use. Be sure to visit plaslabs.com to view our state-of-the-art isolation and containment glove boxes.
Okay, as far as the maintenance on this is pretty simple, but we have to actually shut down the whole system. Many times, in the microbiology labs, they should have a couple of these, anaerobics chambers. Okay, if they, because they have to keep growing the microorganisms, on the agar plates all the time. So in case one unit is failed, you still have another ones. Okay. Okay. The other kind is the apheresis machines, which is the machine that we're using for blood transfusions and or collecting the blood from the patients or the blood donor, something like that. Okay, if you used sometime in the blood bank.
Hi, welcome to another Biomedical Engineers TV video. In this video, we will look into apheresis machines. In this video, we will look into the beginning of apheresis machines, what are apheresis machines, the principle of apheresis machines, and the types of apheresis machines. Let's look into the beginning of the apheresis machine. Prior to the invention of the apheresis machine in 1972, blood had to be collected and mechanically separated into its various components to treat specific medical conditions. This arduous process required a lot more blood to be donated in order to treat a patient with the blood component they required. Thankfully, in the 60s, a man by the name of Herb Cullis came along and began working on a machine that would revolutionize the blood donation process. Cullis was an American medical technologist who knew he wanted to use his skill set to help others ever since he began his studies at the University of Maryland. In 1965, Cullis got the opportunity to do just that when the American Instrument Company hired him and tasked him with building a machine that draws blood from donors, separates platelets out, and returns remaining blood components. By 1972, Cullis was able to successfully build the first blood separator, Thin-Wall CS3000, with 7 other team members. The term apheresis, a Greek word for to separate, was coined thanks to Cullis's work and started to be used as a clinical term in 1979. Let's know what the apheresis machine is. An apheresis machine is a device which receives blood removed from a patient or donor's body and separates it into its various components: plasma, platelets, white blood cells, and red blood cells. Depending on the reason for apheresis, one of these components is isolated and collected by the instrument, while the others are returned to the body. Depending on the substance that is being removed, different processes are employed in apheresis. If separation by density is required, centrifugation is the most common method. Other methods involve absorption onto beads coated with an absorbent material and filtration. Let's learn about the types of apheresis machines. The centrifugation method can be divided into two basic categories. The first method is continuous flow centrifugation. Continuous flow centrifugation, or CFC, historically required two venipunctures, as the continuous means the blood is collected, spun, and returned simultaneously. Newer systems can use a single venipuncture. The main advantage of this system is the low extracorporeal volume, calculated by volume of the apheresis chamber, the donor's hematocrit, and total blood volume of the donor used in the procedure, which may be advantageous in the elderly and for children. The second method is intermittent flow centrifugation. Intermittent flow centrifugation works in cycles, taking blood, spinning and processing it, then giving back the unused parts to the donor in a bolus. The main advantage is the single venipuncture site. To stop the blood from coagulating, anticoagulant is automatically mixed with the blood as it is pumped from the body into the apheresis machine. And the third method is centrifugation variables. The centrifugation process itself has 4 variables that can be controlled to selectively remove the desired components. The first is spin speed and bowl diameter. The second is sit time. In centrifuge, the third is solutes added, and the fourth is not as easily controllable, plasma volume and cellular content of the donor. The end product in most cases is the classic sedimented blood sample with the RBCs at the bottom, the buffy coat of platelets, and WBCs, lymphocytes and granulocytes, PMNs, basophils, eosinophils, monocytes in the middle, and the plasma on top. How does the apheresis machine work? Apheresis units incorporate polyvinyl tubing that draws blood from the patient and moves it through centrifuges and/or filters to separate blood products. The blood is then returned to the patient via tubing or is collected in bags, often suspended from a pole, for donation or disposal. A display and control panel allow the operator to program the unit and view progress and/or alerts. Safety features include pressure sensors, ultrasonic air bubble detectors, optical fluid level detectors, and dry heat fluid warmers. The warmers prevent hypothermia caused by infusing low temperature fluids. The unit may have wheels or it may be placed on a cart. The operator programs the unit to run the desired separation protocol. The unit automatically controls the centrifuge, pump, and other settings. Rotary peristaltic pumps draw blood from the patient or donor and pump blood through filters or centrifuges. Filters separate blood components based on size, centrifuges separate by density. Optical sensors detect plasma cell interfaces to minimize contamination from other components. Centrifuges have inlet and outlet ports and compartments to keep components separated. Pumps move the blood products into collection bags, add anticoagulant, and reinfuse fluids. Replacement fluids, e.g. saline, serum albumin, plasma protein fraction, fresh frozen plasma, are infused into the patient to maintain appropriate intravascular volume and pressure. Let's end this video with the operating steps of an apheresis machine. First, the apheresis machine is wheeled to the bedside or donor chair. Second, the operator connects the sterile tubing sets, also called apheresis sets, to the patient or donor. Third, as the patient's blood is pumped into the machine, an anticoagulant is automatically added and the blood enters the chamber. And finally, blood components are separating using centrifugation and/or filtration. The method of separation depends on the product that is to be removed or collected from the blood. We hope you like this information on apheresis machines. If you like this video, hit that like button and subscribe to the channel. Thanks for watching. See you guys in the next video.
Okay, that's one of the machines that used in the blood bank. Okay, there's a blood bank tissue. Okay, these blood cultures, testing the machines. Okay. This is one of those newer one that actually helped, saving a lot of times in the, blood cultures.
Today, the leader in blood culture instrumentation for the last 25 years brings you the newest innovation in blood culturing. BD is proud to announce the BACTEC FX blood culture system. The heavy demands of today's laboratories call for more than just space-saving instrumentation. Because of our long history in blood culturing, BD understands the needs of laboratory technologists. The BACTEC FX system was designed in response to what our customers have asked for time and time again. Laboratories told us they needed a system with rapid results and maximum performance to enhance patient care. They stressed simple, easy workflow and intuitive data management to maximize their efficiency and productivity. They wanted a system to help them meet safety goals for their staff by reducing the risk of needle sticks and by providing good ergonomics. And finally, laboratories asked for a system with the flexibility to accommodate their changing workload with space-efficient configurations. You'll save space and conserve time for the laboratory staff. Let's look at what's behind the BACTEC FX instrument's state-of-the-art sensor technology. The new BACTEC FX blood culture system is based on the current high-performing and reliable sensor technology that measures CO2 through fluorescence. Every 10 minutes, a precise measurement is taken which can detect changes in CO2 concentration. Advanced signal processing and growth detection algorithms are then applied to determine if a specimen contains viable microorganisms. The utilization of fluorescent sensor technology has proven over the years to be a reliable, accurate process in the pursuit of high performance. The BACTEC FX vial-activated workflow will make your laboratory's blood culture workflow even simpler with an embedded computer and LCD touchscreen. Technologists have an easy-to-use, intuitive workflow, whether they use the system daily or only occasionally. The user interface enables personnel on all shifts with differing levels of experience to master the workflow. The exciting new features and capabilities incorporated into the BACTEC FX make this system one of the simplest and most intuitive available in blood culturing today. With the BACTEC FX, you can feel secure that the unique vial-activated workflow means the instrument knows from the user's first action with a vial what the next step should be. For example, when entering your new culture vials, simply open the drawer, scan the new vial barcode, and place the vial in any available or open location as indicated by the steady green light. You decide where. The BACTEC FX instrument now automatically knows you're entering new vials and brings up the LCD workflow screen for vial entry, all without a keystroke. Sensors in the station know when and precisely where the vial is placed. Those same sensors can verify whether a vial is fully seated in the station and not inadvertently inserted partway. It's all part of the safety we have built into the system. Do you need to remove your negative vials first thing? A negative indicator light on each drawer is automatically lit when there is a negative vial in the drawer. When that light is illuminated, simply open that drawer. Then choose a station that has a flashing green light indicating a negative vial and remove the vial. With that action, BACTEC FX automatically goes into the workflow for removing negatives and lights up only those stations that contain negative vials. No keystrokes are involved. Simply finish removing all of the negative vials. A triple beep informs you when all of the negative vials have been removed. And when it comes to removing positive vials, you'll see that it's just as easy. The BACTEC FX user interface enables all personnel with varying levels of experience with the system to master the workflow. What makes it so easy is that the LCD status screen quickly lets users see the status of each drawer, detailing the number of positives, completed negatives, or the number of open stations. The convenient fill bar graphically shows how full each drawer is. The LCD screen also makes entering new vials simple. In a single motion, you can scan the vial sequence number as well as an accession barcode for patient information. You can also easily enter specimen or patient information right there on the LCD screen. Simply tap on the field and an electronic keyboard appears. No need to pull out a traditional keyboard or go to an external PC. In addition, technologists who use the BACTEC FX occasionally may choose to initiate workflow by choosing simple icons on the screen. Need to remove positive vials? Simply open the drawer and the location of all the positives are highlighted by the well-defined red light pipes. There is no confusion as to which stations contain positive vials. You may remove each positive one at a time, scanning each one as you go. Interruptions are common in the laboratory. Go ahead and close the drawer. You can return later and pick up where you left off. If there is a need to return a vial to the instrument, the procedure is simple and flexible. You can scan the vial and place it back into the same station or into any available station in any instrument. It's as simple as that. You decide. Other aspects of the BACTEC FX that make blood culturing easier are design and configuration options. BD engineers have achieved smart design solutions that work for technologists within the typical laboratory space constraints. Design engineers have given special attention to ergonomics in the BACTEC FX system. You can see how there's no need to reach down too low or up too high when entering or removing vials. The central location of the display touchscreen and barcode scanners also provide easy accessibility and maneuverability for the technologist. The BACTEC FX was designed for maximum capacity with maximum ergonomics in a minimal footprint. The most common configuration will be this BACTEC FX 2-module system designed as a stack. Each module holds 200 vials, and every stack has a single conveniently located touchscreen LCD for the user interface. A barcode scanner is located in both the top and bottom modules. A remote computer screen is available to provide access to the entire blood culture system at the bench or anywhere in the laboratory, preventing interruption to routine workflow. For the higher volume laboratory, BACTEC FX can be configured with fully integrated multiple stacks, as many as you need. This integration allows individual workflow to occur at each stack, while providing the benefits of fully integrated data and reporting. Each stack within this configuration has its own LCD and scanners to provide the ultimate in easy-to-use workflow. There's no need to continually return to a centralized control unit. Integrated data in EpiFX allows the user full flexibility as to where vials are placed throughout the system. Are you pulling a positive here in one stack, but need to check other vials from the same culture or patient? It's easy to do. The integration means you can use the EpiFX remote screen nearest you to view or request information from any other instrument. A third configuration is a single benchtop BACTEC FX to meet the needs of smaller volume laboratories. Data management is one more innovation that sets the BACTEC FX apart. BD recognizes that information is important to any laboratory. So we designed the BACTEC FX to accommodate various levels of data management to fit the needs of different laboratories, whether just simple reports are needed or if extensive lab-oriented reports are required. Remote alarms and remote blood culture observation are available. Total blood culture system assessment is available on one computer screen located at the bench or anywhere in the lab or hospital, no matter how many BACTEC FX modules are present, through the EpiFX. EpiFX provides identical programming available on the resident touchscreen computer in each BACTEC FX stack, allowing for at-the-bench blood culture report generation or observation. The remote alarming system provides easy access for evening and night personnel not located in the microbiology laboratory. With the BACTEC FX instrument's enhanced reporting capabilities, a variety of reports are available to meet your needs. Workflow reports provide you with information about vials recently entered or removed from the instrument in order to assist you with the next step in processing the culture. Historical reports are available that provide information about vials over a period of time, such as all positives for the month or all vials containing contaminants for the month. The BACTEC FX is designed to connect to your laboratory information system. Downloading patient demographics from your LIS to the BACTEC FX eliminates the need for extra data entry. improving your efficiency and productivity while reducing the opportunity for clerical errors. Results can also be uploaded to your LIS if desired. The BACTEC FX was designed to continue the media and performance excellence you've come to expect from the BACTEC line. The BACTEC FX utilizes the breadth of current media, from PLUS and lytic to PEDS, and media for yeast or fungi recovery to support your different patient population and blood culture needs. Historically, BACTEC blood culture systems have always offered you enhanced recovery of isolates from blood cultures to assist in identifying septic episodes sooner, with the same instrument reliability you're used to. The BACTEC FX media bottles easily accommodate safety blood collection sets, thus improving healthcare worker safety. You can use the safety blood collection set with a holder that permits direct draw sampling for blood culture bottles without the need for extra adapters. The BACTEC FX system was designed in response to our customers' needs. Laboratories told us they needed a system with rapid results and maximum performance to enhance patient care. They stressed simple, easy workflow and intuitive data management to maximize their efficiency and productivity. They wanted a system to help them meet safety goals for their staff by reducing the risk of needle sticks and by providing good ergonomics. And finally, laboratories asked for a system with the flexibility to accommodate their changing workload with space-efficient configurations. The very newest in features for blood culture is the BACTEC FX system. It's designed for performance, efficiency, ease of use, and flexibility. Everything the laboratories of today need. The BACTEC FX system can streamline workflow and minimize process steps, two factors that are key to reducing labor costs. Take a good look at the BACTEC FX blood culture system with its impressive state-of-the-art sensor technology, smart ergonomic design, remote observation and alarms, and innovative vial-activated workflow. You'll see that the future of streamlined blood culturing has arrived.
Let's look at the other testing. This is
Welcome to testing with Pogo Automatic. This video will give you some useful hints for testing and is not meant to replace the owner's manual that came with your Pogo Automatic. Let's get started. The time and date menu will appear. Press M when the blinking arrow is next to the clock icon. To adjust time settings, use the scroll buttons and press M to confirm. Use the same steps to change the day, month, and year. To accurately track the date and time of your test results, it's very important that you set the correct time and date before you test your blood glucose. To get ready for testing, make sure there's a test cartridge in the meter. To insert a cartridge, press the cartridge door button and insert the cartridge with the Pogo label side facing you. Next, close the cartridge door. You'll hear a click when the door is closed. While the cartridge is rotating into place, Pogo Automatic is reading the barcode with the calibration information and counting the number of available tests. When you insert a new cartridge, you'll see a 10 in the upper left of the screen. It shows the number of tests that are available. Pogo Automatic uses a very small sample size for testing, only 0.25 microliters, which is about the size of a pinhead. Always wash your hands with soap and warm water and dry them well before you test. Not doing this could affect your results. Since Pogo Automatic collects blood, only use fingers you know bleed well. Avoid calluses and nail beds. To get your finger ready, rub it firmly, starting at the knuckle, and press blood toward the end of your fingertip till the tip of your finger turns darker or reddish from the increased blood flow. Here's another important tip. While you're first getting used to the meter, put it down on a flat surface when you test. Turn on your meter by pressing the power button. Wait till the screen instructs you to begin testing. Then press down on the blue test port with the fingertip you prepared. Make sure to cover the entire opening. When you see the 3, 2, 1 countdown, the test process has started. After 1, the meter will lance your finger. It's very important not to lift your finger off the test port until the up arrow displays. Moving or lifting your finger even slightly before you see the up arrow can interrupt blood collection and prevent you from getting a glucose result. Okay, to recap, put your Pogo automatic on a flat surface. Turn it on. With clean hands, choose a finger that bleeds well and get it ready for testing. Wait till you see the down arrow before placing your finger on the test port. The meter will guide you during your test. Press your finger down on the test port and hold it in place after the lance. Do not lift your finger off the test port till you see the up arrow. You'll see your result on the meter after the 4-second countdown. The next time you test with Pogo Automatic, just remember these hints. For more information, visit our website or get in touch with customer support by email or phone.
Yeah, this video is here. Someone asked about the new it's a blood glucose monitor or testing. So which is very nice that it's have quite a features and quick of testing and history and things like that. So a lot more people switch into this type of device. And some of this device today, it does have like Bluetooth, connected to the phones that have memories, history and things like that to keep track of your health informations.
Professor.
Yeah.
Yeah, it's me. Don't they have like one that I keep on seeing on TV where you don't need to get stuck no more? You just
Yeah, they have it, but the thing is that's they have the patch or some sort of a sensor that you put on the skin that basically that will keep the skin is kind of warm this all the time. Also, there's the thing is you're gonna have to replace that patch on the skin. Also, it's not that's lasts for so many days. So that's something that it's kind of new things, but yeah, you still have to replace that the patch that put on your arms.
So the most accurate one is probably this.
Well,
this one.
yeah, the one that's that stick with just a small amount of blood to be testing.
Okay.
So if you ask me, I say, well, I still prefers the this is the type of we call the gold standard. Yeah.
Okay. Thank you.
Mhm. Okay, let's see this one on this is for the next week's video. Let's see, do we have they have this update one more. Okay, no, I don't have that, which is very short this week. Okay, let me stop this for a moment. See.
Not.
Okay.
Right, here we have a special version of a microscope. This one here you will not find very often. It's the Olympus IX51. It's an inverted microscope. You can tell this because you're looking down here and your objective is right there instead of rather being up on the top. This type of microscope is not just a phase contrast microscope, but it also does bright field and fluorescence. And this one is just loaded with options because you can see it's got the camera. It's got 2 linear actuators. These ones are used for positioning and taking photos in sequence hooked up to a PC. So anyway, this is a very special microscope because it's got an external rear mounted light source. The external rear mounted light source uses a very special XBO bulb and it's like a $700 light bulb. And it's only good for about 500 hours. And you see right here, this is the light bulb power supply. So like a traditional microscope, it's got a binocular in the front, but here you get your down tube. And when you adjust these knobs, instead of adjusting your stage as you would expect a microscope to do, what you're actually doing is you're moving up and down your objective. So it's inverted in almost every fashion. This one's got a camera mounted to the top for recording. Very special microscope. You guys probably won't see one of these very often, but if you do come into it, what makes it very special is this guy right here, which is mounted right beneath your objective. And that's your phase converter is what they would call it. But I can't even pretend to know all the options on this guy because they're so special. You don't see them very often. I just figured I'd show that to you guys since you're probably not going to see them very often. That's the Olympus IX51. A very special microscope.
This is another
Hello,
Nikon.
my name is Stephen Ross. I'm the General Manager of Products and Marketing with Nikon, and we're going to continue on in the microscopy courses with a run-through of the research microscope. And what I want to talk about is all of the components of the microscope and sort of how we integrate it and how you can take advantage of the components on the microscope and the aperture planes and image planes that we've discussed in previous lectures to implement different techniques or applications on the microscope, such as things like building an optical track, building a single molecule total internal reflection system, or even a confocal system. So we're going to start with the transmitted light path on the microscope. The first component of the transmitted light path that we're going to talk about is the lamp house, which is a halogen lamp house on this microscope, and that is removed with one screw here. So this is your halogen lamp house on the microscope, and you can see there's a collector lens in here, and there's actually, you can see a magnified image of the first aperture plane, which is the filament inside that halogen bulb. If we were going to actually take that bulb out of here, we would do that by removing this insulated cover, which is actually very heavily shielded because the bulbs, if they have oil on them or overheat, can actually explode. It's extremely rare, but it happens. But for that, you need to have everything shielded with heavy metal inside the cover of the lamp. And then below that cover, we have this component here. And you can see that this component basically has the halogen bulb held by two metal clips and powered. When you install this bulb in the microscope, you want to actually hold it in the plastic bag it comes in, rip off the bottom of the bag, and then hold down the two clips and put the bulb in and then pull the bag off. You'll never want to get the oil on your fingers on that bulb. That could cause the bulb to fail. Behind the bulb, you see the collector lens that I spoke about before, which is magnifying the image of that filament. Again, that is your first aperture plane in the microscope in the transmitted light system. So next, transmitted light comes through here. This is all aperture space. There's nothing in focus in there, and that's why we put our filters in this location. We've got several filters and a diffuser in this microscope. Anytime you have a halogen bulb or a bulb with a filament, we normally want to soften the edges of that sharp filament. We use what's called a diffuser. And this diffuser is just a frosted piece of glass or plastic. And it breaks down those harsh edges of the filament in the bulb and softens it. We also use a technique called a fly eye lens that instead of having a single filament, we'll make thousands of images of that filament doing the same thing, basically diffusing it throughout the field of view and giving you very even illumination. Then we have several filter holders. There's an auxiliary holder that holds a neutral density filter. We also can use this to hold an infrared cut filter for our dynamic focusing system, the perfect focus, which we'll talk about later. And then on this side of the microscope, we have two other filters. This one is called an NCB11 neutral color balancing filter. It actually looks blue when you look through it. And what that does is it actually takes the halogen bulb, when it runs at low voltage, is more reddish, more orangish in color. And the neutral color balancing filter actually will give you a white background as if you're running the bulb at higher voltage when it puts out more white light. And then we have a green interference filter, which is a narrowband green filter that is used for contrasting techniques like differential interference contrast or phase contrast to give you sharper images, sharper resolution in those contrasting techniques by narrowing the band of wavelengths that you're using to illuminate your specimen. So we come through here. We then have a lens here, which is called your field lens. That's actually in the first field plane of the microscope. And you have an aperture here called the field aperture. Now that's the aperture that we would close when we're doing color illumination of the microscope, and it's controlled right here. I guess I should really call it a field iris, since don't want to confuse the aperture planes and image planes. So the field iris we here in the microscope. Below that, we have the condensing system of the transmitted light path, and we'll start with this polarizer here, which is held on with one screw here. And this is actually a polarizer that can go in or out of the light path. And you can see the polarizer here. This is actually also the compensator of our differential interference contrast system. When you have differential interference contrast, there's many different ways that you can adjust or compensate for the contrast. We use what's called the de Sinnamont compensation, and in that case, we would have a quarter wave plate and polarizer, which is actually sandwiched here in this device, and you can rotate the polarizer relative to the quarter wave plate, and that's going to then allow you to adjust the shadowing or contrast of the differential interference system and change also the directionality. This mount here can be used for other techniques. Many people will use this mount to do things like mount quadrant photodiodes for optical trapping or second detector systems. You can utilize these mounts for those types of applications. Let me also now go down a little bit further. Let me get the covers off the side of the microscope so I can open up the wires, get the wires disconnected. Shield covering the wiring in the microscope. And on that side, and one on this side. Those are going into the hub controller of the microscope, which we'll talk about later. So now the condensing system, the condenser itself, which we call a universal condenser, comes off with a single screw. Remove that now and go through that. So this is what we call a universal condenser. You can see it's basically a turret. It's got a condensing lens on it. In this case, it's a long working distance, LWD, 0.52 numerical aperture condensing lens. And we can put multiple condenser lenses on this, always trading off working distance versus resolution. So if we have 0.52 numerical aperture, it's going to significantly limit the resolution in transmitted light that you can get with, for example, a 1.4 NA oil immersion lens. That's why we make several different compromises. We make condensing lenses that are high NA oil that actually have a numerical aperture up to about 1.4. We make a 0.85 dry, and basically all of these different options will trade off the working distance versus the resolution. This one gives you many inches of working distance, so you can manipulate the specimen, put large specimens on the microscope. So now that we've removed the condensing lens, you can see in here that there's a number of different spots here, and we have prisms as well as phase rings in this condensing system. And this is where you would hold all of your modules for differential interference contrast or phase contrast. You can also see that there is another iris in here, and this is an aperture iris. This is the first aperture iris in the microscope. And that's going to actually adjust the cone of illumination and trade off contrast for resolution in transmitted light techniques. So now we've removed many of the components on the transmitted light arm. One of the last components here is the condenser mount and condenser focus unit. And that just loosens and slides off on the dovetail here. And it's basically a solid brass adjustable mount, and it has a focus on it. And as I had mentioned, this will allow you to mount additional components for doing techniques. So it just gives you a focusability, and it's got it's centered on the optical axis of the microscope. Okay. So we're getting down here. The next thing I want to remove is actually the stage on the microscope. And do that by removing the 4 bolts that hold the stage. There's one here. Okay, another one here. And then 2 in the rear. Just make sure I don't have too many wires hanging out. And we'll lift the stage off. So this stage is actually a fairly heavy and rigid component. Basically, the stage is somewhat simple in that it just has lead screws that move the stage in X and in Y. And in this case, it's got encoders, linear encoders that measure very precisely the distance in X and Y the stage moves and reports back to the software the exact position. This stage is also equipped with a piezo device. So this is a piezoelectric device that gives you 200 microns of Z motion that can be very fast, very precise, synchronized for things like confocal imaging, where you want to do extremely fast Z series and move in Z very repeatably, very accurately, as well as very quick. So now we're really getting down to sort of the base of the microscope. I'm going to take off next the eyepieces of the microscope, and then we'll get back to the light path through. This is what we call the head of the microscope. And basically, it's a set of prisms that splits light to the eyepieces, so you can look in the microscope. And there's really nothing too special about it, other than it's got what's called a Bertrand lens that can be in an open position or a Bertrand position. And what that's going to do is allow you to look in the eyepieces and switch between, in the Bertrand position, the aperture planes of the microscope. So if you wanted to see the phase rings in the microscope, or to check the alignment or adjustment of differential interference contrast, you would be able to do that by looking in the Bertrand position, or you can keep it in the open position. All objectives generally have different locations of the back aperture. So you do have a focus in the Bertrand position so that you can focus at that back aperture plane. And it's got a simple shutter to open and close the light to the eyepieces. Next, I want to talk about the eyepiece itself. So this is a fairly standard eyepiece. It's got a 22 millimeter field of view. And I just wanted to show a couple of things about the eyepiece. The eyepieces are independently focusable. So what you want to do when you sit down at the microscope is close one eye. You adjust the focus on the microscope to a specimen so that it looks sharp. You close one eye, adjust the focus of the eyepiece to the eye that's open, then close the other eye and adjust the other eyepiece. And this way you're going to be able to look in the binoculars of the eyepiece and have it adjusted for your eyes. These are what we call high point eyepieces, and they allow you to use the microscope without having to take off glasses. So the microscope is designed to be used by people with or without glasses and is adjustable, focusable for individuals different eyesight. The other thing I wanted to show you is a area that actually has an accessible field plane inside the eyepiece. And you can see I just unscrewed this little ring, and there's a little shelf inside this eyepiece. And that shelf is where we would put what's called an eyepiece reticle, which is basically a small scale bar that's printed on a piece of glass that we would be able to put onto the eyepiece of the microscope. It's a nice accessible image plane in the microscope, and it's a good location if you wanted, for example, to block certain wavelengths of light. There's other areas we're going to talk about, or if you wanted to, put an IR cut filter if you're doing something like optical trapping and you want to be really careful for laser safety. There's this accessible shelf in there. So you put the 25 millimeter glass in there, and you can screw that back in place and it'll hold a piece of glass in that spot. So next, we have what's called the base unit of the microscope. And that base unit is here. And this actually is all aperture space in the microscope. Some people take advantage of this and place filters for safety or for emission in the microscope, and we'll remove this part with 4 bolts that are here. Okay, so this is basically a large piece of alloy cast, and nothing really too special about this one, but we also make ones that have accessible aperture plane in here where we can put external phase rings or different components that are in an aperture plane in this turret. We also make some that have a slider that allow you to just have a simple slider to put filters or rings within the aperture plane, which is defined right in the center. Below here, this is a relay lens in the microscope where the light will come up through to the eyepieces. And this is also a wonderful place if you wanted to put something like an IR cut filter for optical trapping again, or any sort of a cut filter for laser safety, as well as many fluorescence strategies will have a multi-band mirror to reflect fluorescence up to the specimen, and then have a wheel that will switch channels to get multiple images sequentially on a detector. The problem with those strategies is that you have no barrier filter to the eyepieces. So you could put a multi-band barrier filter here and use one of these fluorescence strategies with an emission filter wheel, and then just have that multi-band barrier so you can look in the eyepieces and see the specimen in the true emission color. So now we're down to, you can see the alloy cast of the main body here. Next thing I'm going to do, just to get it out of the way, is remove the transmitted light arm. We've already gone through all the components of it. Four bolts here. Okay. So we'll take the transmitted light arm off the microscope, lay that over here. So now we're really sort of down to the base of this microscope. Here we have what's called the nose piece of the microscope, also known as the objective turret. The nose piece has a motor in the center, and you can see it holds multiple objective lenses. Currently, it's got one 100x turf lens. Put that off to the side. And then we will remove this component. And I just want to point out a couple of things, because this is not a simple nose piece. It's actually incorporating our perfect focus or dynamic focusing system. There are several different types of systems like this. They work on similar principles, basically trapping the cover slip of the microscope. Just remove loosen up this illuminator so I can get the wire out of the way. One more here. That will disconnect there. And this is our nose piece and dynamic focusing system. So you can see here that there's a cube that goes in and out of place. When this cube is in place, it actually has quite a bit of optics in this side of the unit. It has a laser diode that sends microwatts of infrared light up to the specimen and locks onto the interface of the cover slip and oil, or the cover slip and water interface in an oil immersion lens, or the cover slip and air interface in the dry lens, and reflects back into the system off of that mirror I just showed you, and goes to a linear CCD array that actually knows whether the scope is in focus, whether it's drifting below due to gravity, or whether it's drifting upwards due to expansion of the thermal expansion of the materials, and it tracks that, and it does it every 5 milliseconds. So it's imperceptible to the user, but it'll hold focus indefinitely. And basically, that's all there is really to this component. It's got slots here for your prisms for differential interference contrast. Okay, so now we're really getting down to the base of this microscope. Since I've loosened it all up, let me pull off and go through the fluorescence or epi illumination on the microscope. First, disconnect our light source. We'll go through that in a little more detail. And here is the epi illuminator, which in this case has 2 motors. Pull that off of the microscope. Okay, so this is our epi illuminator on the microscope. And this illuminator is actually a sort of dual purpose epi illuminator. It's got laser illumination on one side, and it would have a laser fiber that would connect a optical fiber that could connect to this FC coupler. And what that does techniques like total internal reflection fluorescence or oblique laser illumination. We also utilize this for our localization super resolution storm technique, and that's this little hatch here actually allows you to drop in a magnifier so that you can magnify the laser beam to give you 1/4 of the field of illumination, but at 4 times, one half the diameter at 4 times the intensity. So 1/4 the field of illumination at 4 times the intensity. The fiber tip here, again, going back to aperture and image planes, is actually sitting right at an aperture plane. And we know that in the case of total internal reflection fluorescence, you need to get a collimated beam of laser light out of the objective. And we do that by taking this aperture plane, where that fiber tip is, and then relaying the core of that fiber tip to the back aperture of the objective lens. And we focus that with this switch here so that we're focused. And then when we translate that fiber in X and Y, it moves that focused laser beam in X or Y at the back aperture, and that changes the angle that the light comes out in image space, because lateral translation in aperture space relates to an angular translation in image space, as we've talked about in previous lectures. There's an optical merge system here. There's a mirror here and then a motorized mirror here, and standard wide field epifluorescence through the other side. And you can see here on both sides, we've got multiple neutral density filters on both sides, as well as an aperture diaphragm on the epifluorescent side. The aperture diaphragm in the case of epifluorescence won't actually change the resolution of the system, but will act more like a neutral density filter and attenuate light, allow you to decrease the amount of light in the specimen. In the case of fluorescence, the molecules within the specimen are actually your source of light. So you're not basically getting an image based on diffraction, but detecting the fluorescence that's being emitted from the specimen. So that's the epi illumination on the microscope. Okay, so now we're really getting down to the base of the microscope. Next component we'll go through is when you have that epi light that comes into the microscope, there's actually a field aperture. I'm going to turn the microscope around the back so that you can really take advantage of this. This is what we call the field iris, and that iris opens and closes and sits in the microscope in this position with the illuminator in place. However, if I wanted to focus something at the specimen of the microscope, knowing that that's a conjugate field plane, I know that if I can focus my light at this conjugate field plane, I will be focused at the conjugate field plane where your specimen is sitting. Okay. So by taking out the epi illuminator, putting this back in, I can use this as a target. And if I set up lasers or optics on a bench and I put a lens here and I focus to that plane, I can get a spot of laser light at the specimen. And why is that useful? Well, if I wanted to do something like FRAP, all I need to do is get the appropriate wavelength of light and focus at the specimen plane. If I wanted to do optical trapping, I would do the same thing with a infrared laser. And if I wanted to make a confocal and I focused at this, I'd have a spot of laser light. And then I could put a confocal or parfocal detector at the image plane on the side of the microscope, which we'll talk about in a little bit, and detect the photons point by point as I move the stage. So a simple stage scanning confocal microscope. Okay, so it's very useful to have these accessible planes in the microscope and know how to take advantage of them for these types of techniques. So that's our field iris. This is what we call the height controller on the microscope. And basically, it's the brains of the microscope. It takes all of the components in the microscope that are motorized and synchronizes them and controls them. And what we would do normally is, with our software, send a recipe for an experiment, say, take one channel image, move a filter, take another channel image, move another filter, and so on, opening and closing shutters for transmitted light, epifluorescence. And we can send all that information to onboard memory storage within this hub controller. And the hub controller then runs all the electronics on the microscope locally, rather than communicating back and forth with the computer saying, open a shutter. Okay, the shutter's open. And that would normally, that type of communication could take a long time. By doing it all locally, we can actually achieve much higher speeds on the microscope to do different imaging sequences. So we'll place this here. Okay. So now, basically down to a block of alloy with one last component, or two last components if we consider the imaging port. So let's just take this off here. And this component is called the epifluorescence turret. And the epifluorescence turret on the microscope basically just holds those fluorescence filter cubes that we've talked about, which will have a dichromatic mirror, excitation filters, and barrier filters, depending on the type of fluorescence filter we're using. The turret, if you see from the bottom, basically is a ball bearing turret with a motor in the middle and can switch the different fluorescence channels here. You can see some filters that are still in place. And it's got a simple hard shutter. If you want to just take a quick look at your specimen, but you don't want to bleach it too much, you can just pop that closed very quickly with your finger. And it's got encoders in it that know what position is in place and reporting back to the software for your metadata. So now we're really down to the base of the microscope, just a little light shield there. And here we have what's called the tube lens of the microscope. And one thing I want to show you, you can see this microscope actually has two different tube lenses in it. I don't know if you can see that very clearly, but we're changing the tube lens in the microscope. In an infinity optical system, the magnification that the microscope achieves is a function of the focal length of that tube lens. So what we do is we have two tube lenses, one at 200 millimeters, which is 1x magnification, one at 300 millimeters, which is 1.5x magnification. And by switching those tube lenses, we can achieve higher magnifications without having to add more glass to the system. Okay. The last component that I'm going to talk about is a relatively simple but very important one, and that is the imaging port on the microscope. Now, everything we do is for efficiency. That's why we use the tube lens method rather than adding a lens to magnify. And we have what's called the side port on the microscope. And then in here, you basically just have a turret of prisms that will port the emission light from the specimen out to cameras on either side or on the bottom of the microscope or up to the eyepieces. And your cameras or detectors would be on this component here called an ISO C-mount. And ISO, standing for the International Standards Organization, sets the specifications of this component. And that's to enable companies like all the camera companies to know exactly where to put the sensor in their cameras. So this is an international standard. And from this flat shelf here to the detector is 17.526 millimeters. And that's actually important if you wanted to do something like build your own stage scanning confocal, because you know now that if you put a detector at 17.526 millimeters from that flat surface, it's going to be in focus on the microscope. Similarly, if you're going to get a spot of laser light exciting the specimen and you put a pinhole that was parfocal or confocal with that spot of laser light and the detector behind that, you could make a simple stage scanning confocal. So the last thing to go through here now is just the fluorescence light source. And basically, this is much more common now than high intensity lamps. There are similar light sources to the lamp house that we showed for the transmitted light. But most fluorescent systems now are using light sources that are remote from the microscope, gets the heat away from the microscope. This one is a metal halide system. We'll show you the bulb. And all the light goes in through what's called a liquid light guide. So the light coming into this aperture is actually trapped through total internal reflection in a core filled with liquid. I believe in this case it's water that would keep the light based on total internal reflection within that core of water into this collimating lens, which is matched to the optics in the microscope and puts a large collimated beam of light into the microscope for epifluorescence illumination. And inside here, we actually have the bulb, just like with the halogen lamp house, very heavily insulated. Okay, and beyond that, we have a bulb that you can pull out. Again, you never want to touch any of these bulbs with your fingers, but you can see this bulb actually has a parabolic reflector around it, and it's a metal halide bulb in this case. We can use LED sources, metal halide, xenon, mercury, and so on. This one again happens to be metal halide. So that's a remote light source, and I think that concludes basically all the components on the microscope. And I thank you very much for your attention.
So that is one is the popular one, also the microscope. And as far as the Nikon, there are several of that microscope that actually popular in the pathology lab. Is the one of the, you know, in the Nikons. I found this in Nikon actually in the university hospital lab or research. It's a lot of Nikons. There's some a lot of Leica. Okay, it's Leica's, you know, it's a lot of Leica's microscope. And also Olympus. Okay, and the Olympus is one of them. That's, you know, all those three, yeah, Olympus, yeah, all those three, we found. Yeah, we found all those three. It used to be the AO, the Americans optics company that make you know, microscope. You know, if you go to some of the lab, you probably can see some of the old the AO, we call it AO microscope. Okay, you know, apparently it's for some reason I think it's they're going out of business. Yeah, they can't really you know, compete with you know, the Germans and the Japanese, you know, companies. So they just went out of business, I guess. Yeah.
Excuse me, Professor.
Yes.
So this is real, huh?
What do you mean real?
No, it just seemed like something that the government would actually buy.
Yeah.
Wow.
But you know, but the AO, the company, I think what they're making today, from what I understand, they only make the like special you know, the aviations, you know, sunglasses for pilot, something like, you know, the yeah, you see some of the Air Force or Navy, and most of the Navy use the AO, you know, or the Air Force, you know. Yeah, aviators, you know, they use that. They still, I think you still be able to buy some of those, you know, sunglasses, you know, for the aviator made by the AO company. I think that pretty much that's what I know of. That's right now. Yeah, that's left over. That's
it seems rather expensive.
I guess so. Is that I think it's probably you know, $200 or $300 per pair. Yeah.
No, I mean that microscope, that was
Oh, you talking about microscope? Yes.
that was like
That is
uh,
very expensive. Yes. Yeah.
very expensive. Huh.
Yeah.
Hmm.
Okay.
In this
Next.
video, I will be discussing TIRF-M, which stands for Total Internal Reflection Fluorescence Microscopy. Let's look at a cell in a traditional microscope. The cell sits on a glass surface in an aqueous environment, and the fluorescent molecules within the cell are excited by laser irradiation that passes through the entire sample. The detector collects the resulting fluorescent signal, from which you can eventually generate a cell image. Now, what happens if you aren't interested in the entire cell? What if you're only interested in the cell's interaction with the glass surface? Is the whole cell body stuck to the glass, or just a certain part of it? This traditional setup is not going to help you answer this question because the whole volume of your cell is being excited and producing the fluorescent signal. This is where our friend E.J. Ambrose comes in, who in 1956 found a way to study the cell-glass interface by controlling the excitation scheme so that only cell parts very close to the glass interface would be excited. He used total internal reflection. Total internal reflection occurs when light is totally reflected off a surface. The Snell's law equation describes the bending of light where there is a change in refractive index passing from one material to another. The variables N1 and N2 are the refractive indices of the respective media, and θ1 and θ2 represent the light's angle of incidence and angle of refraction. If a beam of light passes through glass and then through water, which has a lower refractive index, it will bend to a larger angle from normal. This is easily calculated using the equation. As we increase the incident angle, we will eventually reach a point where the resulting angle of refraction is 90 degrees. We call this the critical angle because once you exceed this angle, you can achieve total internal reflection and the light will not enter the second medium. If the light is totally reflected, then how do the fluorophores near the interface get excited on the other side? Well, it turns out that an evanescent wave is generated at the point of total internal reflection. This energy source decays exponentially from the interface and travels about 100 nanometers up into the second medium, which contains your sample. The evanescent wave excites fluorophores near the interface and ignores anything else, whether it be fluorophores in the cell or fluorophores freely diffusing in the solution above. TIRF-M works for samples that fluoresce and are close to an interface. There are several different geometries that can be used for this technique, and I will be discussing the two most common, prism-based and objective-based. Prism-based was the first type of geometry used for studying interfaces. This is traditionally built with a non-inverted setup, meaning that the objective lens that collects the signal is located above the specimen, which exists in an aqueous solution sitting on top of a glass surface. The excitation beam passes through a prism situated with the sample to hit the glass-water interface past the critical angle and create the evanescent wave. Note that the excitation and emission parts of the microscope are situated on opposite sides of the sample. This allows the objective to collect only the fluorescent signal. Unlike p-TIRF, objective-based TIRF has an excitation and emission parts of the microscope situated on the same side of the sample. In fact, they share the same objective lens, which sits below the sample in an inverted configuration. Excitation light enters the objective lens off-center so that it can be sent at an angle to hit the glass-water interface. Because the critical angle of glass and water must be exceeded, O-TIRF only works if the lens has a high numerical aperture of at least 1.34. The evanescent wave is generated and the fluorescent signal travels down the objective with the reflected laser light. The excitation and emission sources are separated by a dichroic mirror, allowing only the fluorescent signal to reach the detector. Both p-TIRF and O-TIRF can be used for nanoscale and single molecule imaging. Let's discuss the pros and cons of TIRF-M geometries, specifically with regards to stray light artifacts, sample and technique flexibility, and cost. To get really nice nanoscale images, one wants to minimize any stray or scattered light that might cause artifacts in detection. In this category, p-TIRF is the preferred geometry. In p-TIRF, stray light can come from scattering at the glass-water interface or at the prism. Because the collection objective is rather far away from these sources, rarely are extra measures necessary to minimize stray light. O-TIRF, on the other hand, is more prone to stray light. The figure here identifies several sources in the O-turf setup that can contribute to significant stray light interference. This can be minimized by optimizing the optics, particularly the objective lens and the dichroic mirror. Additional filters can also help remove the excitation wavelength and scattering. However, P-turf is often described to have a clean turf and better signal-to-noise ratio in comparison to O-turf because of its natural lower stray light interference. When it comes to sample flexibility, O-turf has the advantage. The O-turf setup is naturally inverted, meaning that the objective can connect nicely with the bottom of the slide through oil immersion. This makes collecting near-field signals straightforward. P-turf, on the other hand, has the evanescent wave generating on the opposite side of the sample, away from the objective. This means that the fluorescent signal needs to pass through the bulk of the sample to reach the objective. Alternatively, if you want to put the objective below the system, the prism is in the way. This is going to limit near-field collection. The whole P-turf setup can be inverted, but when this is done, some limitations to sample preparation ensue because the sample holder is now upside down. Another fun thing about O-turf is that it is friendly with other analysis techniques. Because O-turf geometry is confined in the objective lens itself, resulting in free space on the stage, O-turf can be combined with other nanoscale imaging techniques. It has been shown to be used with fluorescence resonance energy transfer and atomic force microscopy. P-turf does not work well with these other techniques because the geometry is bulky. When it comes to money, P-turf is by far the financially friendly option. To get a high numerical aperture objective lens capable of pulling off turf, you must be willing to spend a couple $1,000s on the objective alone. P-turf does not require such expensive lens because the critical angle is achieved with a prism. Interestingly enough, P-turf microscopes were commercially unavailable and had to be self-constructed in research labs until quite recently. Many argue that the commercialized microscope companies aiming to make money preferred to offer O-turf setups because they would require the purchase of the pricier objective lenses.
Okay, so that's another kind of, yes, okay. There are so many different kind. I think it's, if you look at on the ACRI paper or reading paper, that I think is on one of this file, you're gonna see it. It should be right here. You go to on the side, you probably will see a lot of those. And maybe a microscope, if you look, see. Right. Okay. Hang on. I think it's do we have one more? And this one. Oh, a couple more. Let me see what we have there. Oh, the mechanical, this is a medical the isolations. I have this video show that's the isolation transformer system that we use for when we have the medical device that have a high leakage. So we're gonna use that this medical isolations power system. Okay, but this one is kind of long video, so I'm gonna skip that for now. All right. And this one is only 14 minutes, so let's look at this scale, repair and taking apart here this assembly on the digital scale. All right, that we have a lot of those in the lab. Okay.
Hello, everyone. Welcome back to Better Biomed. Today, we're going to take a look at digital scales and what makes them tick and some of the similar functionality between scales. So let's dive right in. Coming up next, right here on Better Biomed. we have here is an OHAS digital scale. OHAS is a very well-known brand, and their scales come in all different shapes and sizes. This is a typical benchtop scale that has got an AC adapter and it's got alkaline batteries underneath. Some of the functionality of the scale, there are leveling feet around the corners, and you see right here, there's a leveling bubble. So you can zero your scale before you take your measurements. Front control panel are membrane buttons. And one thing that you should note about all these scales is that they always have their maximum rating someplace on the label. Either it's on the back, usually on the front. This particular scale is rated at 8,100 grams, which is just over 8 kilograms. So this is a pretty hefty little guy. On top of the scale, you have a platter. They're almost always removable. Underneath that is a platter adapter. Here, we are down to the meat and taters of the scale. Once we remove this plate, we're down by the load cell. I'm going to flip it over. Take out these batteries. One of the problems that we constantly have with scales is that the users tend to leave the batteries in over a long period of time. And if you're running your scale off an AC adapter, there's no sense in having batteries in it at all. But here we are. You can see how the leveling feet function. These ones here are hiding the fasteners, which hold the whole scale together. One of the other common things that we have to deal with is that users tend to lose or break the leveling feet. So if you're ever turning in a scale because something's broke on it, try and keep the feet. You'll need them later. To me, like I have some torques. First guess, love that. Right. See one of these fasteners. As you've seen, this scale had an error code on it, which is probably why I found it in the disposal bin today. So we're going to take a look at the load cell and see, maybe we can figure out what's going on with that error code. Maybe we can fix it and get the scale back up and going. As you can tell, it's not that old of a scale.
All right, let's see what's happening there. Let's see. The issue with the internet. I don't see.
I think so. That's what happens normally.
Yeah. But my internet is still working, still connected. Okay.
Maybe it's being buffered. Yeah, go back.
Joins the control panel to the control board. Great. See, I have one power input output board. Or input output? No, it's just input output. So there is a serial port on the back of this guy, which means you might be able to have accessories like printers, or you might be able to take the serial data stream out and incorporate it into other applications. So that's my I/O cable. Here is my DC adapter. And you can see it also ties into the battery. All in one plug. It's very efficient. Let's take the shield off. I have never taken one of these scales apart. Please forgive me if something breaks. All right. It's an interesting shield. I don't know if that is used for shielding the measuring components. I would assume so, since we're dealing with such minute values here on this load cell, which that is what we're dealing with. I'm going to pull this load cell out so we can see it, and then I'll explain to you guys what a load cell is. Okay, I've got my cables here. Yes, I'm not using torques. You understand that? Right off the bat, I do not see any physical damage that would have caused an error code. So maybe by putting this all back together, I'm going to solve that problem. Go. Body off to the side. We can talk about the meat and taters of the scale. All right. This is a load cell. And it works on a very simple principle. Let me pull this top part off so you can get a better look. Well, that is on there tight too. I can tell you. This piece here is just an adapter. It's a cone. It's nicely up into the platter. That's all it is. All right, so these ones here are apparently bump stops. So we've got bottom bump stops and top bump stops for whatever reason. Probably because these scales go through a lot. Here we go.
Put on too much weight on it.
It's really interesting that they put a circuit board on the load cell itself. That's probably why OHA scales are so accurate, because they want to place a component that does the measurement as close to the analog device that creates the signal. So there we go. It's got your limiting screws. I'm definitely not going to touch those for their adjustments. This is a load cell. And what we have up here, yes, this is a fully functioning one too. So what we have here, these are strain gauges. See here, here, and here. And you see how it's got that dog bone. Because as you place a weight on one side and the other side is anchored down, what it does is it creates a compression on one side and an expansion on the other side. Opposite side of the load cell, you get expansion and contraction, compression rather. So you have 4 points of measurement, which
give you a very stable reading and a lot of resolution. Now, these load cells use a circuit called a Wheatstone bridge. And what you're doing
just to move it up some, baby.
is you're actually balancing out adjacent corners for expansion and compression. And you can actually see, let's take a look up here. Camera picks it up. Yeah. There's little grinding marks inside right here, tiny little grinding marks, because what they did is they removed some material here and here to bring it within its calibrated value. That's actually really interesting. It's a sloppy way of doing it, but that's definitely a sure way, because what happens is as you add tension on one side and you get compression and you get expansion, well, that's going to change voltage measurements. These are going to be an analog signal, and they're going to come here to a board that's going to convert them to a digital signal, which is why I was referencing that they placed the board that's going to do the analog to digital conversion as close to your analog sensors as possible. So this is a load cell, and these are strain gauges. There's 4 of them. It's very cool.
Well, if you remember, you know, we talk about this in the early, in the electronic 34 and the transducer.
This principle is going to be used in all sorts of digital scales, from the large ones that weigh trucks, like semi trucks. Not kidding. They use a system very similar to this, and depending on
Because I think it's right now it's I know it's quite a windy in my areas. That's my cause from that you know, the internet cable, something like that. Yeah, because that's what happened.
the scale is 8,100 grams. So this is probably rated at what, 10 kilograms, I bet, 10 or 20 kilograms. Very, very neat. Let's see if it comes in so you guys can
Yeah,
see.
and then many times, you know, if somebody, you know, put something very heavy, you know, overload that, this load cell that can be damaged, the load cell also.
Digital board.
Was that why they had those stops in there?
What?
Was that why that they had those stops in there? He was saying they had like a stop post, so it could only go down but so much.
The scale.
Well, yeah, I mean, that's the thing is this, you know, when somebody puts that so heavy and then for so long, that could cause the damage too. And yeah, we see people, you know, puts the stuff and, you know, use the stuff on the
some load cells only have,
it's like a storage areas, you know.
Yeah.
Is a full bridge, just like a full bridge rectifier that you find for AC to DC conversion. This is a full bridge because there's 4 strain gauges. This is actually very interesting. So you can technically measure these to see with ohms to see if they were close in tolerance. If you have one of these little strain gauges that's got a much larger ohms value than the others, then that's going to be your problem. This is going to be a throwaway part, of course, unless you really exchanged. Take a look at that. There's a serial number.
and a part number right there on the end cap. So that digital scale. Nothing too fancy. Up here, you got your membrane buttons, which go to your controller for the membrane buttons. And all they do is relay back to your processor. So the processor is doing the comparison of your load cell on the Wheatstone bridge, and it's also taking your commands from the membrane buttons. Pretty simple. Nothing major there. So guys, that is a digital scale. I bet you didn't imagine it's something so simple. You have them in your kitchen, you have them in your bathroom, you have them in hospitals, you have them in railroad stations. Digital scales are everywhere, and they use a very similar principle. So now you know what makes up a digital scale. That's all I have for you guys. I hope you like this video. Give me a thumbs up if you do, and subscribe to the channel, because 70% of you guys that are watching these videos are not subscribers, and I hope I earned your subscription today.
Okay. All right. So I think that's pretty much that's it for today. All right.
Hey, see, the question for you, sir.
Right.
A guy like that, is he like an independent repair person or?
Oh, the